Hello, everyone. This is Boqing Gong from Google Research in Seattle. I will talk about when and how vision transformers can outperform ResNets without any large-scale pre-training or strong data augmentations. I will start with my PhD training. When I started my PhD training, I worked on Bangalore models for visual recognition. But soon after I graduated, my former students and myself, we started to work on convolutional neural networks, of course, on all different visual recognition tasks. But more recently, we moved on to vision transformers and vision multilayer perceptions. So very interestingly, we have fewer and fewer inductive biases in the neural models. For example, for vision transformer, just to make sure we are on the same page, here is a very quick review. It's published earlier this year by my colleagues at Google Research, the Brain team. Basic idea is given input image, we partition it into small patches, non-overlapping, and then we go through a linear projection layer followed by precision encoding. After that, basically the very vanilla transformer architecture will be applied. It has self-global attention across all the patches, and at the very end, it has a global representation for the input image. The precision encoding is necessary because the pixel information really cannot tell which patch or which position that patch comes from. The network is interesting because it removed the convolution. So basically, there is no locality or translation equivariance inductive bias in the model. As a result, it's able to take advantage of the large-scale data and the pre-training better than ResNet does. Here shows that if we do the pre-training of the model on large-scale dataset, and then we fine-tune the model on 5 different downstream tasks, and we take the average of the accuracy here, show the figure on the left. Or we can do the fine-tuning on ImageNet, showing on the right. So you can see the blue dots are the results of vision transformers. They are significantly better than the ResNets. ResNet here shows the gray squares. What this figure here tells us is VIT is able to scale with the data and number of computation better than ResNet does. Why this matters? Why does this matter? Well, if we look at the recent datasets, which roughly represent our community's research interest, we have really high ambition. We want to recognize everything, right? So from the beginning, Office 31, this is the dataset I worked on the most when I was a PhD student. We moved on to 1,000 classes in ImageNet. We have more than 8,000 classes in iNaturalist, and the full ImageNet dataset has more than 21,000 classes. So this is the number of classes, not talking about like instance recognition, such as face recognition or landmark recognition or some detection datasets. So we really want the visual models to be capable enough of recognizing everything. We want to scale up our model's capability. And in order to achieve that ambition, we need new models, new tools, new techniques. From the figure earlier, it showed that likely VIT, maybe not likely, but at least VIT is a very promising technique, very promising neural architecture for us to scale the model with the data and to achieve the ambition. That's one of the reasons I feel VIT is exciting. It's exciting, it's able to scale because it has fewer inductive biases. And also the large-scale pre-training actually could be amortized by fast transfer. So in the fine-tuning stage, for different classes, maybe you only need a small fine-tuning dataset instead of a large one. So that's that's kind of like amortizing the cost of the pre-training. Furthermore, the capability of being able to scale up with the data is evidenced by the powerful language models. So that's one of the reasons I feel VIT is able to scale with the data and able to recognize millions of classes and instances in the future. So another reason it's exciting is we can envision, because VIT it's very powerful in NLP. Now it's able to recognize a lot of objects as well, could become a centralized model, which basically takes different modalities as input, but the model itself maintains the same, at least for the architecture is the same, and it produces versatile representations. So this can really simplify a lot of real-world applications in terms of model development, deployment, maintenance, and upgrade, and a lot of things. So it can save us a lot of engineering effort. Meanwhile, if we could have one centralized model to take care of different modalities, we can transfer the knowledge between different modalities. There is one catch. There is one catch if you check the paper. The catch is the VIT is really data demanding. The authors pre-trained the model on the full ImageNet with more than 21,000 classes, and the second version of the model was pre-trained on GFT with 300 million examples. And there is another, there is an alternative to make VIT work on the medium-sized computer vision dataset. The paper was from Facebook and Sorbonne University. But the problem there, at least I see it as a problem, they have really strong data augmentations and regularizations. Also, they need very careful combination of them, meaning that we have a lot of hyperparameters. They are combined together, and it's really hard to tune. Also, although the title suggests that it's data efficient, to me, maybe it's still not data efficient, because given all the strong data augmentations and their combinations, effectively, we are still learning from a lot of data. Also, it's not very transferable, because the domain knowledge about images may not transfer to videos, to point clouds, and other data. So given new modalities or new domains, we have to redesign the data augmentation techniques. So given all those observations, our objective in our project is we want to get an accurate and robust VIT on the ImageNet 1000 without any large-scale pre-training or strong data augmentation. So if we train the model on ImageNet 1000, the training set, and we tested on the validation set, we got the accuracy. But we also tested on some robustness datasets, including ImageNet R, ImageNet C. There are quite a few real-world perturbations to the validation examples, or some additional validation examples from different distributions. Their purpose was to test the models out of domain generalization. We call those as robustness here. So this is experiment setup. How should we achieve that? The basic idea is it's straightforward, actually, because we know the original experiment setup here that convolutional neural networks are already able to work really well in this setup. So when we try to achieve the same thing by VIT, well, we can learn from convolutions. We tried to analyze what are the differences between VIT and convolutional neural networks after they converge in terms of the loss landscapes and overfitting. And also, before we train the model, we also analyzed the differences in terms of so-called trainability. What really matters in this talk is the first aspect, the loss landscapes. I will, at the very end, show the paper. So if you are interested in the other aspects, I mean the overfitting and the trainability, you can go and check the paper. In this talk, we focus on the loss landscapes. So you can see after they converge on ImageNet, ResNet, the local minimum is quite smooth. It's much flatter than the local minimum of VIT. Of course, the visualization could be kind of not the faithful representation of the high-dimensional space. So we also computed the Hessian matrices after they converge. The dominant eigenvalue of the Hessian matrices tells like how sharp the local optimum is. And you can see VIT has a really large eigenvalue here. It shows indeed VIT converged at a much sharper local optimum than ResNets does. Well, our hypothesis, therefore, given that observation, we conjecture that maybe we can try to improve VIT's generalization capability by making sure that it converges at a flat region instead of a sharp region. And in order to achieve that, there are actually quite a few different techniques to do that. We chose SAM, it's called Sharpness Aware minimization. The basic idea is, okay, when we try to minimize the cross-entropy loss, we try to minimize with respect to the kind of adversarial around a region. So around a region of the parameters, W is the weight of the network. Around that local region, we find the highest error, and then we minimize that error. So the total effect is that within that region, hopefully at the very end, the loss and every single point in that region is very small. So ensure, at least in that region, the loss is flat. The loss landscape is flat. There are some theoretical guarantees. It shows that the generalization of a deep learning model indeed depends on the concepts of flatness. And the algorithm to solve this is fairly straightforward. So it's basically parameter randomization in the training stage, except that we do not randomly add perturbation to the parameters. Instead, we adversarially add some perturbations to the parameters. So I will skip the algorithm here. Instead, let me show you the results. We compared vision transformer with ResNet here. Actually, ResNet has in this figure has way more parameters than VIT. So without looking at the model architecture, you might be wondering that ResNet probably will overfit the model, the data, because it has more parameters than VIT does. But the reality is different, because VIT really does not have that locality or translation equivariance. So it's actually overfits the data quite severely, and the generalization is not very good on ImageNet. But after we train the model using the SAM optimizer, so at the very end, it converges at a flat local optimum. Very surprisingly, the improvement is so significant that it's able to even outperform ResNet. Of course, okay, you may ask, that's not a fair comparison, because what if we train ResNet using the SAM optimizer as well? As you can see, here we show the results. Still, it's not be able to catch up the performance of VIT. This is not surprising, because although ResNet can still benefit from the SAM optimizer, but the inductive bias essentially reduced the search space in a certain region in the high-dimensional space, like a 300 million dimensional space. It reduced the model to only a small region because of the inductive bias in the model. But VIT has more freedom to explore the search space. We show more results in the paper. I will skip the table here. The basic idea is VIT outperformed ResNet of similar sizes in both accuracy and robustness. Here, we got the results without using any large-scale pre-training or strong data augmentations for both VIT and ResNets. Also, we showed that by using the flat or sharpness aware minimization after the model converged and a flatter region, the attention maps in VIT also showed more perceptive segmentation information than the attention maps trained using the traditional SGD, which minimize the cross-entropy loss only. Okay, to summarize, the main message in the paper is the following. We have VIT and vision transformers and vision multilayer perceptions, which I find them exciting because the general purpose architectures might be able to connect different modalities and even different communities, even more smoothly than the traditional neural architectures. Also, the sharpness-aware minimization turns out a very data-efficient approach to learning VITs. Its potential, I think, still is unexplored. So it's interesting. Would be interesting to investigate it further, or similar techniques, which not only some, but similar techniques that are able to promote the flat convergence local optimum for different models. We showed improved accuracy, robustness, transferability, and attention maps in the paper. We also did some analysis showing what are the intrinsic changes after we trained the model using SAM. One thing interesting was it has much sparser activations, especially in the first few layers. So if you're interested in this point, I encourage you to go read the paper. It's on archive now. So the whole project at the very end, I feel it's something we can summarize as, given new model architectures, we need new learning algorithms to fully uncover the potentials and fully leverage the potentials of the models. I did the presentation, enjoyed the presentation, but actually Xiangning Chen did all the hard work. He was a student researcher, and also before that was an intern with me at Google Research. I also want to thank his supervisor, Chou Jui Xie.